So let me start again with the geometry of the Rindler wedge. You can see. So here is the, I wrote already this blackboard, so we gain a little bit of time. So these are the Rindler coordinates we were discussing last time. At the beginning, you consider real coordinates, psi and eta. Psi is positive. And they cover, at the beginning, only this region of the Minkowski plane. Of course, you think also of x and y variables coming out of the blackboard. So that the Minkowski geometry has this form. These are the coordinate system which are tailored on a uniformly accelerated family of observers covering this wedge. So these two lines act as horizons. This is the past horizon, this region you cannot see, and this is the future horizon. In this region you cannot send signals. Okay. One technical, very important step is to pass to light cone coordinates. So they are defined as, you know, as the difference and the sum of the time and space variables. And so if you input the definition of the Rindler coordinates in here, you see that u is a negative coordinate in this wedge, because u is minus psi e to the minus theta, and then you take the logarithm and you put into the exponential, and you call capital U this quantity. Of course, this is an exponential, so it's positive in itself, but there is this minus sign here, and therefore this is a negative coordinate in this wedge. In the same way, V is a positive coordinate in this wedge. Now you want to extend your coordinate system to the Minkowski manifold. So the easiest, yes?
You wrote eta twice in each line.
Sorry?
You wrote C plus I eta, that's
here.
Eta plus I rho.
I'm sorry, zeta. So this is the second, thank you. The second second important step. You can consider this manifold being in itself a globally hyperbolic manifold. Means that you give your Cauchy data on this surface, you can completely solve your Klein-Gordon equation in this region if you just give your data on this manifold. So it's a globally hyperbolic manifold in itself, but you can consider it as a complex manifold. So consider complex Rindler coordinates, okay? And you ask yourself if there are other real sheets of this complex manifold. So the first sheet that you obtain is region 2. If you give those values of to so take psi equals 0, so a total imaginary Rindler coordinate I zeta, and rho equal minus ip over 2, you see here that this is a second real sheet of your complex manifold. So do this little computation, and you see that you get zeta cosh eta here, and zeta sinh eta as zeta. So if you compute the metric here, you see, where you wrote psi square, Now you have I zeta squared. So this changes sign, also this changing sign, so they are interverted. This means that what was a space-like coordinate, psi, now is a time-like coordinate, and vice versa. Eta is a space-like coordinate in this second region. This metric is no more static. You see, it depends on the time coordinate here. If you apply the same definition to the complex variables here, you see that the phases add up in the first u variable. So you get plus ip over 2 plus log of an imaginary thing that gives a log of a real thing plus a positive thing plus ip over 2. So this is ip, and there is this minus sign. The minus sign disappears, and you get that u is positive, while the phases cancel out in the v, it stay positive. So in the extension we are doing in this region, we get positive u and positive v, and u equals 0 is your past horizon. So the past horizon is covered by u equals 0. So this is, you take the same definition, take ip over 2 here, minus ip over 2, purely imaginary here, and you are covering this region. Okay, this is the Milne universe. But what is most important is that we can go in the left region. In the left region, the situation is simpler. You get a zeta equals 0. So pure real psi coordinate, and minus ip or plus ip, depending on which path you follow in the complex manifold. So what is the total, the net result is that you have changed this sign. So you see that what is a positive time in this region becomes, it goes in the other way, in the opposite region. This is the important fact you learn from here. And if you compute the u and v coordinate in this region, now the phase stay in both cases. So ip is going to change both sign. And so you see that in this region, you get positive u and negative v. Okay? As much for the geometry of the complex Rindle wedge, but we need one final thing, is that to express u and v in terms of u and v using this relation. So we get here in region R, we have u is minus log of minus u. Remember that u is negative here. And v is log of v. And since u, so we get that u is eta minus log psi, v is eta plus log psi, eta is u plus v, which is log v minus log of minus u. This is eta in region R. This is the crucial formula, by the way, to derive the Unruh effect. And in region L, so this is region R. In the region R, we got that U is e to the U, and V is minus e to the V, so that in region L we get V is minus log V minus log of minus V, and U is log U, and therefore eta, which is defined in the same way in region L, is log U minus log of minus V. Okay, if I'm not wrong.
Should there be a factor of 2 somewhere?
Okay, 2 eta, yes. This is 1f.
So that would be half U plus V, or?
Half U plus V, yes. Okay, thank you. So let me verify this formula. Okay. So now we are going to this formula is there. We keep it in mind. We will use it later. Now we consider quantum field theory in the Rindler wedge. Okay. So at the beginning, we quantize our theory just in this region. Okay. Doing this, we are going to use the Rindler coordinate system in the original region, and write this equation in the Rindler coordinate system. If we proceed the standard way, unfortunately, so the modes, we separate the equation in the Rindler coordinate system. So we, if we write the modes as positive frequency modes with respect to the Rindler time, okay, and a trivial part depending on the transverse coordinate, and a function which depends on the psi coordinates. If you separate this equation in the Rindler coordinate system, we saw last time that you are going to get the Bessel differential equation. Okay. This is we already did this computation the last there is xi square here. We did this computation last time, just express the Klein-Gordon operator in the Rindler coordinate system. We choose positive frequency with respect to the Rindler time and separate the variables in the obvious way, we get the Bessel differential equation, and then you have to use the recipe of canonical quantization to normalize the function f. The function f is just the McDonald function. You take your preferred book in special functions, and there's everything about the Bessel functions. My preferred one is Bateman, volume 2. Or you can use the Watson book, a treatise in Bessel functions. Okay, and there's a formula in the Bateman book that tells you the measure, the vector normalized to this surface is 1 over xi d eta. And there is a formula in the Bateman book that you can try to prove that tells you that the integral of t minus 1 minus epsilon k I omega 1 t k I omega 2 t dt of, if you prefer, t to the minus epsilon dt over t. This is gamma of epsilon I omega 1 plus omega 2 over 2 square gamma of epsilon plus I omega 1 minus omega 2 square over 2 divided by 2 to the 3 minus epsilon gamma of epsilon. If you let epsilon go to 0, you get the delta function out of here plus a normalization. This formula you can find in the Bateman book. You can prove yourself this formula knowing the properties of the McDonald function. And you see that you get here a family of normalized modes which are written this way. The normalization, by the way, is irrelevant for our computation, but let me give you the full answer. U omega of k, depending on the variable eta, xi, x, and y, is hyperbolic sine of p omega over 2 pi square e to the minus e omega eta e to the I kx. I mean, this is a 2 vector k of I omega square root of m square plus k square psi. These are the normalized modes. The normalized modes which have been normalized on this surface with the Klein-Gordon product. The only formula I did not show to you is this one, which I used, picking it in the Bateman book. But I urge, you know, once I was doing a computation for my research, and I picked a formula in the book of, there's a 5-volume book, Marichev, of special functions. And I picked one book in the 5th volume, one formula. And I start using this formula to prove a special case of my problem. And then something was going wrong with this formula. So I wrote to Marichev and asked him, could you please provide a reference for that formula? And he answered to me, that formula is wrong. It will disappear from the next edition of the volume. So never trust a formula in a book. By the way, in Bateman's book, there are mistakes, but they are listed. So here, this is the final answer. If you now superpose the modes by summing up u and u star, as we learned, of psi prime and the other variables, this is, provides a quantum field theory in the Rindel wedge, and this vacuum is known as the Fulling vacuum. Okay, so this is what a Rindler observer could call the vacuum. Of course, you can start playing around with Bogoliubov transformation inside this, this family of modes, but you cannot recover in this way, just starting from these modes plus the Bogoliubov transformation. You cannot reconstruct the Weizmann vacuum of Minkowski. I will come back on this point at the end if I have the time. How you can construct the Minkowski-Weizmann vacuum just using these modes. Now we go this historical way, and we follow the idea of Unruh, which is, we want now the question we want to answer is, what does a Rindler observer see while looking into the Weizmann vacuum? Is there any question?
No, just a clarification. That's good. Yeah.
Okay, you're right. So we are now we take the viewpoint of such an observer, but we don't want to use this vacuum. We want to answer to the question what this observer see in looking to the Weizmann vacuum.
Sorry, the C in the argument of the K function, should it be squared?
No.
It was squared in one of your earlier formulas.
I'm sorry, there was a mistake in one earlier formula. Here there is psi, and this is the momentum, k squared plus m squared. Okay, so we are constructing these modes, e to the minus e omega eta times something. Okay, these are the positive frequency modes with respect to the Rindler time. But we want to construct a Bogoliubov transformation that transforms the standard Minkowski modes into this one. So if you try to do it directly, you go by Fourier transform. But the argument used by Unruh is to compare modes that have the same analyticity property. And we saw that these modes, e to the minus ekx, their analyticity properties is in the backward tube. You can summarize this property by saying that these modes are analytic continued to imaginary of the time negative. Okay, this is the prescription, let's say, which selects the right properties, the right analyticity properties, so which uniquely select one particular family of modes. And this you can see if you go back to the light cone variables. This is equivalent to asking imaginary of u negative and imaginary of v negative. Okay? So we are going to glue together the right modes. These are the right modes. And the left modes, which, the point of the discussion we had before is that right modes are positive frequency with the minus sign here, and since the time runs backward in the left wedge, left modes are positive frequency with the plus sign here. Okay? But how do? We use those formulas. and we proceed by analytic continuing this into this, following a path that goes from a region here to a region where we are on the cut of the logarithm function, in such a way to keep always the imaginary part of u and v negative. Okay? If you do this, it's extremely simple at this point. So you get, you have to follow e to the minus e omega eta, and you see that eta is this difference of logarithms. Okay? Go with the log from this region where log of u, log of minus u is minus u is positive. You give an imaginary part to u and v in such a way to keep negative sign to the imaginary part. You see that there is a cooperation between these two, log u and log v, in such a way that here you're going to get e to the minus e omega eta minus pi omega. Right? Because you get, because of this 1/2, your colleague was pointing out, you get minus ip over 2 for each of those. Because the phase of the logarithm here is minus ip. And since of the 1/2, you get minus ip over 2. So you are going to map your mode, right, into a mode which is defined this way. You write in the right wedge, and you left star, because you have to change the sign of eta is not changed, and you get e to the minus e omega eta times e to the minus p omega, and then you have to provide the right normalization. Since these modes are orthogonal with respect to the Rindler calculation, because one is non-zero here and the other one is non-zero here. But when you use the global surface, you have to divide by the sum of the norms. And so you get here a normalization which is 1 minus a to the minus p omega to the minus 1/2, because u and u star have opposite sign in the normalization, okay? 1 over minus p omega to minus 1/2, okay? Because UR is as norm 1 here, and UL as norm minus 2 omega, 2p omega. You see? The norm of this is 1. The norm of this is minus e to the minus 2p omega. So you have to divide with this, and this is a family of modes which are normalized on the full Cauchy surface and which have the same analyticity properties of the positive frequency modes of the Minkowski spacetime. So this is one family of mode, and you get a second family of mode, which is, so the normalization, I wrote it here. And the second, you start, of course, now from the left wedge. You get, so, a second family of mode u left, let's call it like this, which is u left divided by 1 over 2p omega square root. And you write star, same, a to the minus p omega, 1 over a to the minus 2p omega. So what are, let's do a summary. Yes?
Sorry, should there be a 2 to the in the exponent of the normalization factor of UR?
Here, yes. So the only thing you need to know is what is the time component what is the part which depends on the time variable of the modes. Then you follow the analytic path, which is the same path of the modes A, Kx, means imaginary of the time, negative. Of course, these are analytic in a much larger domain. And so you construct the analytic continuation on the second region of these modes, passing from the imaginary of time negative. And you get a second family of modes doing the opposite, starting from here and going to here. And you can verify that those modes are complete with respect to the Klein-Gordon product once defined on the whole Cauchy surface. Of course, if you take these modes on the half Cauchy surface, they will be over-complete. Okay? That's why there are two family of modes here. Now, the problem is solved, because having written this, we can write the Bogoliubov transformation that goes from one family to the other. Are there questions? If not, let's continue. So what we are doing now will be the model to solve the Schwarzschild case, which is more subtle from the physical point of view. Mathematics is more or less the same. Okay, so let me remind you what are the formula for the Bogoliubov transformation we are going to use. So we wrote, we can use one or the other way. I choose to use this way of writing. This is for the Bogoliubov transformation, and the vector, the vacuum, is written in terms of the new vacuum. Okay, so this is the formula we are going to apply. Using those relationships, we see immediately so let me call this mode U1, not to make confusion with this left and right that are here. And this mode U2, these are Minkowskian modes. Minkowskian, I mean positive energy modes. So U1, U2, let's write the upper part of the matrix. So U1 is going to be, so here we have U right, U left, U right star, and U left star. Okay? These are the Rindler modes. The right mode, the left mode, the star right mode, then the starlight modes. These are defined. The right mode is defined in the right wedge. The left mode is just defined in the left wedge. And these are the modes we are constructing by gluing the modes together. Okay? So what are the coefficients? There is the global normalization in phase of everything, because it multiplies everything, the normalization. And then U1 is 1 here, and U star left, e to the minus p omega here, 0, 0. And U2 is 1 here, e to the minus p omega here, 0, 0. And so alpha is 1 over 1 minus a to the 2b 2 pi omega 1, 1. This is alpha cross, but as you see, it's symmetric and real. So alpha cross is equal to alpha. And beta minus beta is a to the minus p omega. This is extremely simple. We will see that the Sparship case is a bit more complicated, but the principle is exactly the same. Okay, so we are going to compute this S matrix here. Are there questions? So that minus, we get the matrix minus beta star alpha minus 1. Alpha minus 1 is just 1 over n. 1 over n erases this. Minus beta star alpha minus 1 is the matrix e to the minus p omega, e to the minus p omega, 0, 0. Okay? This is the matrix which is going to enter in the Bogoliubov transformation here of the state. So let's do it quickly. In the end, we get, so the determinant of the matrix alpha is the square of this. Since it's in the denominator is 1 over e to the minus 2p omega square root. So the Minkowski vacuum can be written in terms of the Rindler left and right vacua in this way. It's the product over all the states, which we label with an index j, 1 over 1 to the 1/2. Okay. And then the sum over j, a to the minus p omega j, a dagger left j, a dagger right j, applied to the Rindler vacuum. If you make a series expansion of this, you get 1 over n factorial e to the this e to the n pi omega j remember that n, the normalized state, is 1 over n factorial over square root. But since we get here from 1 over n factorial, so we get 1 square root to one state and 1 square root to the second state, the final answer is this. 0 Minkowski is the product 1 over n to the minus 2p omega j e to the minus beta, and there is no beta here, n p omega j, n j left, n j right, because they enter with the same power, these things.
So where's the sum and product? Are we not just applying that formula?
Here I wrote a transformation mode by mode, omega j by omega j. But in the end, we have to sum over all the omega j's.
Oh, so up there.
This depends on j.
Oh, okay.
jk, k. Okay. All the modes. There I did not write everything. Okay, yes.
So the product is only over the square root factor, and summation is over everything to the right of it?
Everything depends on j. The product is over j.
Yes, but which part is product?
This is a sum. This is a product. Everything is in the product. Mode by mode. Okay.
Sorry, what did you say the summation is over?
The sum is over nj here.
Oh, okay. Sorry.
Okay, sorry. So this is the final answer. But if you want to get the final answer, now we have expanded the state, the Minkowski state, by using the left and right modes of the Fulling vacua. But we are an observer who is moving in this region. So we have no way to measure particles which live in here. So we are going to compute this state and take a trace of the state over the left part. Okay, this means bracket that big thing. When you write 0 Minkowski this way, you get two products here, two sums. But when you bracket with the same object, because you are going to take the trace, this forces these indices to be the same. So when you take the trace, the square is going to disappear from there. So you get product j 1 over a to the minus 2 pi omega j. The sum is square a to the n 2n p omega j, n right, nj right. The product is over the j, the sum is over the nj's. Okay. This is the final answer, the really final answer. You see, this is a density matrix. If you compute the trace of this thing, it's 1. So when you trace this result expresses the Minkowski vacuum state as a combination of the Rindler vacuum states as a Bogoliubov transformation. Then you average over all the states which are here, and you get a density matrix and a thermal density matrix. This is summarized by saying that a Rindler observer sees in the vacuum, if he is moving with his own detector, sees a thermal distribution of Rindler modes at the temperature. Of course, we are used here eta as time, but remember that eta is the acceleration times the proper time. So this tells you that the acceleration is, the temperature is a over 2 pi. Okay. So, summarizing, we start from the Rindler wedge. We construct positive frequency modes with respect to the Rindler time. We extend to the right wedge deconstruction, to the left wedge deconstruction, and then we glue together those modes in such a way to respect the analyticity property, which is the same of the Minkowski case. And then we compare the modes which we have glued this way with the original ones. Doing this, we implement the Bogoliubov transformation because we are able to compute this transformation. The S matrix is going to express the Minkowski vacuum as a superposition of Rindler states. Then you trace over this part and you get the thermal spectrum. We are now going to do the same thing in the Schwarzschild case. And then I will leave the word to, so I continue without break, do the Schwarzschild case in the same identical move, and then we have a break, and then Matteo will tell us something more about the Schwarzschild case. Are there questions here? I will send you the notes with the whole calculation, by the way. Maybe I did something not completely precise, but you'll find all in the notes.
Okay, so here, right, we're assuming our when we do that trace, right? So, okay, if this observer sees accelerating in a space-time, right? He looks at the field, he sees
he cannot see anything from here. It is covered in the past and in the future.
Right. So he's in the right wedge, and he sees the temperature, he sees the field at the temperature of a over 2 pi, his acceleration.
Yes.
And when we calculated that, we traced out over that left region, which was, we defined in some way, we defined our horizon assuming he was going to be accelerating for an infinitely long time. So in some way, like, if he sees a thermal bath with that spectrum, he knows he's going to be accelerating for an infinitely long time because we've traced.
Of course, this is unphysical. No one can accelerate for an infinitely long time.
Yeah, but I just mean, like, in some way he's already knows he's going to be accelerating for an infinitely long time.
If he knew he was in the Whiteman vacuum.
Yeah. Okay. So.
But what he sees is just a thermal bath. By the way, you can ask yourself, what does a Minkowskian observer see? Because there is someone going around here accelerating. But here there is some guy sitting here and looking also, no, moving this way. What does he see when this thing? Well, he sees something also. When this guy absorb a quantum from the thermal spectrum, if you make the calculation, if you go on and complete the calculation, you can see that he sees this absorption as an emission. He's emitting a quantum, and we will discover that the quantum emitted by the detector, which is always accelerating, is localized here. That's what he sees on the Minkowskian one. So there is no creation of energy, by the way.
Right. Okay, I gotta think about it.
Think of it. We'll discuss on Wednesday. So let me go on and explain how the computation is done in the Schwarzschild case. So the first step is to construct the coordinates. The analogous of these coordinates were crucially used in the analytic continuation. So you know for sure, but if not, I will tell you or remind to you what is the fastest way to construct the cascade coordinates in the Schwarzschild geometry. So you start from the Schwarzschild metric. So something is going wrong at r equal to m. So you need to construct a new coordinate system to get rid of this oddity. And the first thing you do is to introduce the tortoise coordinate. How do you say in English, tortoise? Tortoise. Eddington-Finkelstein coordinate that is defined by taking this differential element. You integrate it, and you get that the definition of R star is R plus 2m log of R over 2m minus 1. Okay. What is the advantage of the tortoise coordinate is that now this surface has been pushed back to R star equals minus infinity. So this is the advantage. Now R star is a variable which covers the whole real line. So this is the first step. Now so if you write the metric in this coordinate, of course, is this. Here you cannot be dispensed with the radial part because it's going to play a role also. In the second step, you move to light cone coordinates. I'm sorry, you will see this asterisk going up and down continuously. It is just a random motion. Pass to light cone coordinates. Okay. So you want to remove this thing from the metric. So let's compute it using the relation there. We make the exponential R star over 2m is the exponential of R over 2m, and the exponential of the logarithm is R over 2m minus 1, okay? Then multiply this equation by 2m over r, 2m over r, 2m. When I multiply here by 2m over r, I get 1 minus 2m over r over r. And so I computed this 1 minus 2m over r. 1 minus 2m over r is 2m over r. The exponential r star is b minus u over 2. And then I get this exponential of minus r over 2m. Okay, so if I use this in the metric, I get that ds square is 2m over r e to the v minus u over 4m, e to the minus r over 2m, du dv minus r square d omega square. So you see, this problem has disappeared from the metric here. And now the horizon has been pushed to minus infinity here. You want to keep it back to a finite value of the coordinates. So you define u equal a to the minus u over 4m and v minus a to the v over 4m. If you do this, this metric becomes 32 m cubed over r, a to the minus r over 2m, du dv minus r squared d omega squared, where r is intended to be a function of u and v. These are the classical coordinates. And now you can extend those coordinates in very much the same way as we did in the Rindler case. So we are here in this region. Big U is negative. Big V is positive. They are the analogous of little u and little v of the Rindler case. Okay? This is the surface U equals 0. This is the surface V equals 0. Okay? And then you extend to other values of the u and v variable. Here u is positive and v is positive. Here u is positive and v is negative. And here u is negative and v is negative. Of course, there is an important difference. R equals 0 is mapping to these two surfaces, which are true singularities of the matrix. Okay? So we get the same structure of the Rindler extension in these coordinates big U and big V. There is the singularity located here. And we discovered that also in this case, there are two horizons. The surface R equal to 2m is made of these components. So, okay. This is the first geometrical thing. Now, the second important part is that in the discussion, we will rather think in terms of the Penrose compactification of this coordinate system, because we are going to study the massless equation in the Schwarzschild region. Okay? And because the equation is massless, so here there is a Cauchy surface. Okay? This Cauchy surface, this is the Schwarzschild region. This is the Cauchy surface, which is represented here as this surface. But since we are just describing this, of course we can also discuss the. I assume you're all familiar with the Penrose. No, this is the. You are right here. Then you compactify this thing, pass to tanh or u tilde and tanh v tilde. Okay. In this way, you shrink the possible values of u. Let's say u tilde is tanh u and v tilde is tanh v. You make a mapping in which coordinates which can have infinite values are reduced to finite value of the coordinates, and you do this in such a way that this amounts to a conformal transformation of the metric. So when you throw away the conformal factor, you get that this infinite space-time is represented as a finite piece of paper. So these parts are, this is the singularity, r equal to m. This is the infinite, okay? And this point is also infinite. So this is the horizon, h plus. This is the other horizon, h minus. This is called, for a reason which I ignore, scry. Scry is light like infinity. Scry minus is this boundary at infinity. Scry plus is this boundary infinity. Is the locus where the light-like trajectories end. So we have a structure at infinity which is this way. This is time like infinity, these points, I minus I plus. And you get the same thing on the other side. So you see, this is the Penrose-Carter diagram of a black hole. This is the Schwarzschild region. This is the region, this is what you call the black hole. This is the singularity inside the black hole. This is what you call the white hole. So from the white hole, things can only emerge. Things can only get into the black hole. And there is a copy of our universe on the other side. This is the maximal extension of the Schwarzschild coordinates. All right? So the point is that having represented the Schwarzschild geometry by its Penrose diagram, we see that since this equation is massless, we can deform the Cauchy surface, and we can impose initial data on these two boundaries, the past horizon and scry minus. The difference is that we do not need to say anything about this point. If we were in massive case, since this is time-like infinity, we should say something here. That's the difference. And asking, the question is what an observer sees outgoing here at late time. So we are going to compare our initial data here, which this is what we are going into the black hole. We will take a trace on it, and we will see what an observer sees outgoing here by doing the same thing we did in the Rindler case. All right? Okay. Of course, you don't really put your thing. Then you can deform this surface, of course. So if you want to give things at finite time, you need to specify also part of things like this. But we will do this in a short while. So we are going to use this as a Cauchy surface. No need to say anything here, because since we are doing the massless case, every massless trajectory, every light-like trajectory intersects this surface or this one. No trajectory intersects this one. Okay. So this is the geometrical setup. Is there any further question? Is everything clear? Yes.
This works like the things you're describing here works in the 1 plus 1 dimensions, right?
No, this is I mean the radial part. You can think of a sphere attached at every point.
Okay.
We need it, by the way.
It's just wait.
I'm describing the 4-dimensional case.
I'm just thinking about if you have a ray with non-zero angular momentum, wouldn't that change its radial velocity, I guess you could say?
We are expanding everything in spherical harmonics, so we gave a complete description of this. Okay, so we are doing the 4-dimensional case. Otherwise, you do the hyperspherical harmonics, of course. So this treatment is for the 4-dimensional case, but The angular part is, I mean, if you go to the hyperspherical harmonics, it's treated the same way, but I don't know how the equation changes, because in 4 dimensions, we will see that the equation is extremely simple. So let's do this. Now we are going to consider, precisely as before, the problem of quantizing this field in the Schwarzschild part of the diagram, okay? But of course, we will need to do an analytic continuation here. But we are beginning here, okay? So first, let's discuss first the shape of the equation. Now we are going to write this equation in this region using T, R star, theta, and phi as coordinates. If we do this, we will see, and we suppose that U has the following form, let's say phi, the modes are the following form, U of L of T and R star over R Y L M theta and phi. Okay, an expansion in spherical harmonics, and we divide by R. If we divide by R, that equation becomes simply this equation. This is true either in the massive or in the massless case, of course. This is an equation for UL. The simplification occurs because we have divided by R. Do the calculation and you will see that this is this operator, or you can even put an M, and you get a potential here. The potential is going to depend on the angular momentum. It has the following form. The centrifugal term, the Schwarzschild term, and eventually the mass term if you are studying the massless case. This is the potential. This is just an easy computation of expressing the D'Alembertian in the Eddington-Finkelstein coordinates and input an expansion into spherical harmonics. So you see this potential, but of course you have to think of R as a function of R star. Means that this potential is defined in the region R bigger than 2m, okay? We are studying the Schwarzschild part. We are out of the horizon, okay? Outside. So if you look at this potential in the R star coordinates, if you go back here, where it is, you see that 1 over 2m over R is essentially exponential. Put R equal to m here, R equal to m here. 1 over m over 2R is the dominant part near the horizon. Means that the exponential is exponentially, R is negative, exponentially small near the horizon. So indeed, near the horizon, this is just a massless wave equation. And also near plus infinity, then you get some inverse power of the radius. So in the end, we are studying, if we now impose a dependent positive frequency with respect, or negative frequency with respect to the Schwarzschild time, we get a Schrödinger problem. a Schrödinger problem in a potential which has this shape, exponentially vanishing here at R star going to minus infinity, and vanishing as an inverse power at R star going to plus infinity. Okay. So we can use see a scattering from a potential in the Schrödinger picture. The problem is reduced to this. This part of the problem is reduced to this. And so you can solve this problem by the methods of scattering from ordinary quantum mechanics. You get an ingoing wave at minus infinity, an outgoing wave at minus infinity, an outgoing wave at plus infinity, an ingoing wave at plus infinity. Okay? Yes?
Can you repeat what you said about what did you do with the e to the I omega t?
You write here. You get here. We wrote a function ul of r star and t, and you write it as a to the minus e omega t or plus omega t ul of r star. And then for this part, we get a Schrödinger problem. Okay. So we can write the solution f ul r star at minus infinity as a minus in the ingoing wave e omega r star, because at minus infinity you just have plain waves. Minus infinity is the horizon, plus a minus out. This is at the modes going into the horizon, e to the minus e omega r star, and the same. This is near minus infinity, and this is near plus infinity. The same solution, near plus infinity, is written in terms of coefficient, which are a plus out ai e omega r star plus a plus in. This is the ingoing wave going into the potential. Okay. But the equation is linear, so these coefficients are related by a linear transformation. Maybe I can erase this. I don't need it anymore. So we get that we are almost there. Right? I mean, once we have done this, we are ready to compute the Bogoliubov transformation and see that there is a spectrum which is almost thermal. So this is solution expressed here. This is the solution expressed here, and you know that you can write a plus out, a minus out as S, the S matrix, a minus in, a plus in. Okay, because you need just 2 of these numbers to determine the solution, and you have 4, so they are related by a linear transformation. This has to be, by conservation of probability, has to be unitary, right? Compute the probability by using the Klein-Gordon product, and you see that this has to be a unitary matrix. And then here comes another important point. By time reversal invariance, of the equation, not of the solution, of the equation, time reversal invariance of the Klein-Gordon equation if you time reversal invariance means that f is a solution, f star is also a solution. So if you take the star of all of this, you get mapping that A minus in is mapped into A plus star.
Should it be a plus or minus?
This is minus, sorry. We are here in the minus region. Okay. So this is a little computation. If you compare this with the fact that the star is also a solution, you get a relation that tells you that S times the matrix 1, 1, 1, 1 equal to S transpose S. Something like this. Let me check. This is time reversal invariance. Okay. So this imposes that those two coefficients are equal. These are the transmission coefficients. Time reverse invariance means implies if you use this relation, you will see that S11 equal S22. And if you use here, you put 1, 0 here, you understand that this is the transmission coefficient. Here you get the reflection coefficient. And by unitarity, apply this other restriction, you get the coefficient that enters here is T over T star, or the other way around, R star. Okay. R is you have a wave that enters, you have a reflected wave and a transmitted wave. And of course, T square plus R square equal 1. This is unitarity also. Okay, T over T star, R star. So if you see that if you have an incoming wave that is 1, 0, you get T and R as transmission and reflection coefficient. If you have an incoming wave which is 0 and 1, means that the incoming wave is not this way, but is this way. So it comes from infinity, not from the minus infinity. In the case in which you enter this way, the reflected wave has a weight R, and the transmitted wave has a weight T. In the opposite way, if you apply this to this, but you better use a phase here. You put here T star over T, which is just a phase. You get that the transmitted wave has coefficient T star, and the reflected wave has coefficient minus R star. We just used unitarity and time reversal invariance for this S matrix. Okay. Now we are ready. We just need to specify how do we build our in state. So once more, this is the Schwarzschild part of the Penrose diagram. So we have scri minus, scri plus, H plus, H minus, H minus, H plus. Okay. And then these horizon are, yes.
Sorry, the diagram there, did you switch the in minus and the out minus?
Sorry?
You labeled the arrows in minus and out minus in that diagram there, but is that the correct labeling?
These arrows?
Yes.
This is the in the region in where R is towards minus infinity, R star. This is the out wave in the region where R star is minus infinity.
Oh, sorry, I'm used to in and out meaning something slightly different.
In is the wave, and minus is where we are.
Yeah, sorry.
So, as I told you, we will use modes which are normalized on these light-like surfaces, even if the surface is at infinity. Okay? So, the point is, what is the prescription? There are two natural prescriptions here. Remember that this is the U equal 0 surface. So little u is also constant on these surfaces. And little v is constant on these surfaces. So the natural thing is that we use the Schwarzschild notion of time at light like infinity. So the in modes, the in modes here are positive frequency with respect to the Schwarzschild time. So at minus infinity, light like infinity, you get V. Is it clear why V? Because U does not vary on this surface. So V is the time there. Same thing here. So this is U, this is Scry, Scry minus. And the same natural choice. So a Schwarzschild observer at infinity is a Minkowskian observer, and you see positive frequency waves, which are, I mean, when I say equal, I don't mean equal. There is also the part which depends on R star, of course, which will make precise. Same thing here. You get U, okay? So e to the minus e omega v here, e to the minus e omega v, and this is just means positive frequency in the Minkowski sense, or the Schwarzschild sense, which is the same here. Now you should need a prescription here and one prescription here, okay? The point is that whatever is your prescription here, it's irrelevant, because those modes are entering in the black hole, and you're going to take a trace at the end. But what you do here is relevant, because these modes are going to be either scattered into the black hole or propagated to the infinite. And those are will be seen by the Schwarzschild observer at infinite. So the point is, the whole discussion on the Hawking radiation is what you put here. So maybe after Matteo will tell us more about this point. But the point is that if we are thinking in this way, we cannot really solve the problem of black hole radiation, because the past horizon, if you are studying a collapsing star, is not there simply. So the whole analysis of Hawking and of Bourou also in their original papers consists in comparing something you do here with something you do in the background of a collapsing star. So this description is non-technical, it's physical, it's based on geometrical optics. And the end of the discussion is that if you think of a mode which enters in the background of a collapsing star, what happens? There is an horizon which is forming. So these modes enter here. stay there for a long time, and then they are scattered to infinity. There is an argument based on geometrical optics that says that this process, which is a physical process, is equivalent in this diagram to choosing modes which are positive frequency with respect to the big U variable. Okay, I'm summarizing the result. I'm not explaining to you the geometrical optics argument, otherwise it takes me an hour. But you can read the argument in the original paper by Hawking. This is the non-technical part of the paper, but this is the insight. Okay, you can discuss it, of course. You cannot not believe it. But this is the argument. If you accept the argument, we can continue. So we are going to use modes which are positive frequency with respect to the U variable. Look that I put here an omega prime. But I have to do this now. The point is, how do we do this? We do this in the same way in which we computed the Unruh effect. I don't use directly the U variable, the big U variable, but I'm going to use the little U variable. So you see, here I have e to the minus e omega u, and I'm going to glue together e to the minus e omega u with e to the plus e omega u on the other part of the horizon in such a way that these right modes and these left modes are glued together according to the prescription imaginary u negative. Is it clear, the logic? I cannot use directly the u variable. The calculation will not be possible directly. I have to use the little u variable, which are the variable that come in at the horizons, here, omega u, at the scry. But I have to glue together those exponential in such a way to respect the prescription. And the prescription is that positive frequency with respect to the big U variable. So you define on this horizon, let's say the left mode, the right mode is right mode on H minus. I'm sorry, there are a lot of things. I'm not writing omega here, but I should write also omega. This is theta of minus u. Remember that here u is negative. Theta of minus u e to the minus e omega little u. Okay. And here, the left modes on H minus, this is the minus horizon, are theta of u e to the I e omega u. In such a way that when I glue these things together with the right phase, I get something which is analytic in the lower big U plane. Is it clear? The same I did in the Rindler case. Yes?
I'm sorry, these are both H minus modes?
These are modes on H minus, yes. H minus is this horizon here. Normalized on H minus. So those modes are non-zero here, 0 here, and 0 here. These modes. These modes are non-zero here, 0 here, and 0 here. And these modes are non-zero here, 0 here, and 0 here. Okay? And then I don't do it again. I mean, I tell you the result. The result is that gluing these modes together amounts to choosing the right weight. And if you go back to the definition of the big U variable in terms of the little u variable, which unfortunately I erased, is the same in which we did have in the other case. Log of big U is minus over, there is a 4 pi m. Do you remember the definition? So if you go back to the definition of the role of the acceleration now is played by a factor of 4 pi m omega. So I get the modes 1 on the horizon minus, which are u right on the horizon minus, plus a to the minus 4 pi m omega u left on the horizon minus, divided by 1 minus a to the minus 8 pi m omega square root. These are the modes. These modes are now defined on the whole horizon minus, okay? And they are correctly normalized there. And I get analogously a second family of such modes on the horizon minus, which are defined in star, of course, because there is the same phenomenon. The time u goes in one way in one direction and the opposite way in the opposite wedge. And the second, you interchange left and right, minus plus a to the minus 4 pi m omega u right star h minus divided by 1 minus a over 8 pi m omega 1/2. And then the third mode is u theta minus, u sky minus, which is just a to the minus e omega v. These are the modes entering, defined here and here, okay? And then we have the outgoing modes, which are defined here. This is e to the minus e omega u. And then one is defined here. And we take for commodity the same which is here, just propagating it, e to the minus e omega v. This is the first one. So I have a family out now. I have the modes which are physically interesting for us, u over sky plus, which is essentially e to the minus e omega u. Then I have a first mode on h plus, which is defined only on this half of h plus, which is the same which enters from here, e to the minus e omega v. And I need another mode here, and I can take whatever I want there. And I take the same that I put here. The second mode on h plus is u left on h minus. I take the same. In this way, the computation is the simplest possible. The simplest possible. Okay? So now this is the in vacuum. You get the vacuum, you put what is now the logic of the computation? We put the system in the vacuum. The vacuum in, let's say, which is annihilated by the operators I theta minus, A H minus 1, and A H minus 2. Those operators annihilate this one. And then you want to write the Bogoliubov transformation, trace over everything, and see what an observer at infinity sees. Because you were in the vacuum at the origin, and you collect a radiation at plus infinity, you say that the black hole is radiating. You see? So the difference, we are not considering a maximal analytic extension, which would be the Arthur-Looking vacuum. In that case, we will have also radiation entering. Here we don't put radiation entering, and because of the Hawking arguments, we are describing a process in which something is sending radiation out at infinity with nothing coming in at minus infinity, okay? So the thing is now here, and we need just one last thing. We need to re-express the in modes in terms of the out modes. So there are two possibilities. One is this process here. You have the U right modes. This is the reflected mode, and this is the transmitted mode. So we get that U right equal to U right H minus equal to T U scribe plus R U 1 H minus. This is this analysis. We are doing scattering theory in the Schwarzschild region. So I don't have, here I don't have any thing coming in from the left region, just the right region. This is the process in which I put an in mode at minus infinity in the radial variable R star, and I get a transmitted mode plus a reflected mode. This is the first possibility. And the second possibility, I have an entering mode from sky, which is partly reflected and partly transmitted. So I get U delta minus sky minus equal T star because of time reversal invariant U1 H minus minus R star U sky plus. Okay. So these definitions plus scattering in the Schwarzschild region allows us to write the Bogoliubov transformation. It's already written there. So we can write now U. I will give you the result now without, maybe just write the Bogoliubov and then the result, which is the same. At this point, we are not, I mean, the calculations are precisely the same as before, with the difference that we have in the calculation now more degrees of freedom and this transmission and reflection coefficients. And we will get a thermal radiation only when the reflection coefficient is 0. Otherwise, the body is not black. There's a spectrum which is non-trivial. Okay. So how it works, as before, here, let's do one of these things. So U1 H minus. So we are going to write a Bogoliubov transformation this way. U1 H minus, U2 H minus, U square minus, and then U, okay, this is enough, equals A as before, cross minus beta transposed, and then I put here the degrees of freedom which interest was U square plus, U1 H plus, U2 H plus, U square plus star, U H plus 1 star, U2 H plus star. And so in this way, I can identify the matrices alpha and beta just reading from these two blackboards. For instance, what do we have for u? So alpha, let's compute alpha plus. So we have here H1, H minus. It has u, this, let's call this normalization n, and this e to the minus beta omega, okay? So u minus is ur h, but ur is t uj plus r uj plus. So I get t times the normalization, because the square plus. Then I get r times the normalization. And then I get nothing more in the alpha matrix, because this is going to enter in the beta matrix, this term, u star. Okay? This is 0. This is alpha. And then you do the same. You understand that the logic is the same as before. So let me just give you the results. Alpha is n so I have here the result for alpha. Alpha is n, everything depends on omega, as before. 0, 0, 0, n omega, the normalization, minus r star omega, minus t star omega, no minus, 0. This is alpha, and this is beta, n minus 1 t omega, 0, minus r star, n minus 1 t star omega, r star omega, 0, t star, 0, n minus 1. Now this is alpha minus 1, I'm sorry. I'm copying the wrong line. Beta is 0, 0, n to a the minus beta omega, a to the minus beta omega, t star, a to the minus beta omega, r star, 0, 0, 0, 0. In such a way that alpha minus 1, the thing which is entering in the Bogoliubov transformation, the matrix minus beta star alpha minus 1, is, as it should be, a symmetric matrix, you remember? And with this matrix, we are going to use the same formula as before and write the vacuum, the initial vacuum, as a Bogoliubov transformation of the out vacuum Let me just give you the final result. It's the product over omega, 1 over n omega, let me give you the final result in the product form. So let's write the final formula. Completely 1 e to the minus a pi m omega sum and omega e to the minus 8 pi m n omega 1 over n factorial t omega a dagger theta plus sky plus r omega a dagger this is already traced. I already taken the trace over the modes entering in the 2 region. This is already the trace. This is the final result. The same thing, the same operator. Okay, so we write exponential of this matrix I dagger minus beta star alpha 1 a dagger 1/2. This is the result of last week. We apply this to the out vacuum. The normalization is 1 over alpha, the determinant, to the 1/2. And this is the in vacuum. Okay? Here you get the operators of creation, alpha dagger sky, alpha dagger H1, and alpha dagger H2. The alpha dagger H2 is creation of particles which are inside the black hole, you see? Because this is the part of the horizon which is inside the black hole. Okay? H is H minus inside the horizon. So we take the trace over those modes and we get this density matrix. Okay? In this density matrix, we don't have already taken trace on the modes entering in the black hole. If you do, you finally get a result, which I write as an exercise. You can trace over. You see, the trace here is a little bit more complicated because you have the sum of 2 operators. And when you take the trace over this operator, these the states which are relative to this operator, in the end you get a density matrix which is relative only to the particles which are escaping at light-like future infinity. And this is as the form, the product over all the energies, the sum over the modes at a given energy, and omega sky plus a matrix here, P and omega, that depends on the temperature, n omega sky plus, and this matrix P, you can, if you compute this sum, is you have to play around with the Newton binomial. I will send you the whole calculation by mail. So you see, this matrix, the theory is thermal only when t equal 1 and r equals 0. It's exactly thermal. Otherwise, it's not. Okay. But what matters me is the principle of the whole thing. there are the prescription is always related to the analyticity in a certain variable, okay? And then you make the Bogoliubov transformation by computing the coefficients of your transformation, make the exponential, and take the trace over the states which are beyond the horizon, or which enters into the horizon. And this is what an observer at infinity sees, okay? Why these things is going on this way? Because we are in a collapsing star background, and modes that enter in the star which is forming the horizon can be scattered and get to infinity at arbitrary late times.
Are we in a collapsing background? When we first wrote down the metric, it was static.
No, we are not in a collapsing background. The part of the explanation I didn't give is why being in the collapsing star, but maybe Matteo will tell us something now, while being in a collapsing star background is equivalent to putting this prescription here on H minus. This is the physical idea. But then we use the classical coordinates. This is based on geometrical optics. This is written in the paper by Hawking. But this is non-technical. It's just an argument concerning the fact that this particle has infinitely blue shifted entering there. So you can use exponential approximation for those waves, and you see that this is equivalent to this prescription. But this is indeed a physical argument, not a mathematical proof. Yes?
I'm sorry, I'm not sure. This thing we've constructed, is it the Hawking vacuum or the Unruh vacuum? Well, part of Hawking.
This is not the Arthur-Hawking.
It's the Unruh vacuum?
It's the Unruh. Classical. I would call it classical. The Arthur-Hawking would be a black hole in equilibrium with the radiation. Here there is no equilibrium, indeed. Nothing enters, something gets out.
So you have a static black hole at radiation.
I mean, I don't do here the computation of the back reaction, of course.
Right, okay.
The topical point is this prescription here. This prescription is supposed to be equivalent to describing something which is not on this background, but is in a background in which you don't have a past horizon. And there is a future horizon which is forming at a certain time. But I didn't tell why it would have taken me too long a time. And you see an argument which you can read without doing calculation. Okay, so that's much for what I wanted to say. And then maybe 5 minutes break and we continue, if you agree.
It's noon?
We have 3 hours today.
Okay.